Welcome to the deep dive. Today, we're cutting through the noise on one of the biggest bottlenecks facing advanced AI, long horizon reasoning. You know the scenario, right? You ask a large language model to do something simple, immediately calculate interest, and maybe summarize a paragraph, and, well, it's flawless. But then you ask it to handle a complex, multi-step process. Think like a long, dependent math problem or debugging code across several files, where an error in step one just breaks the entire chain. That's when the model often just collapses. It struggles with the depth of the sequence. So we're tackling this head on today. We're diving into a paper that introduces a pretty neat scalable method called H1. Our mission is to understand how these researchers managed to teach LLMs to reliably handle these complex sequences using, and this is the interesting part, surprisingly simple, existing training data.
And this isn't just some, academic curiosity. LHR, long horizon reasoning, it's the absolute foundation for pretty much any high-value, complex AI application. We're talking about automating research-level mathematics, maybe assisting in scientific discovery, or even designing robust AI debugging tools. It's fundamental. The traditional methods we have, well, they're incredibly costly. They either rely on humans providing really expensive supervision at every single step of the reasoning chain.
Which just doesn't scale.
Exactly. Or they require sophisticated sort of auxiliary models just to verify intermediate steps or context. And neither of those approaches scales efficiently at all.
Okay, so we need a method that teaches this deep reasoning without that constant, costly hand-holding. We need to figure out how they bootstrap these complex, long-horizon skills using only readily available, simple data.
Right. Let's maybe start by just nailing down the terms. Long horizon reasoning, or LHR. It requires the model to correctly execute a deep, multi-step reasoning process. The ultimate goal, whatever it is, has to be intelligently decomposed into smaller steps, and those steps have to be executed successfully, often in a chain of thought or COTI. And the critical part here is that these are dependent tasks. The output of step one becomes the input for step two, and so on. If the model messes up early,
The errors just snowball.
precisely, they compound sometimes exponentially down the line.
And reinforcement learning, RL, I mean, it's been powerful for boosting general LLM performance, right? But the data limitations have always been the sticking point for LHR specifically.
That's it. Existing LHR training data. It's scarce. It's expensive to create. And even when researchers do use it, the model performance tends to hit a ceiling pretty quickly. The data sets just lack the sheer volume and, crucially, the progressive difficulty needed for deep learning in this area.
So that scarcity problem is what H1 is designed to tackle.
Exactly. The core innovation really rests on two pillars. First, something they call chained problem construction. They take short horizon problems, think standard sixth grade math questions, like from datasets such as GSM-8K, and they synthetically compose them into arbitrarily long chains of dependent steps.
Okay, composing simple problems into long ones. What's the second pillar?
Second, they use curriculum learning. They employ RL, but, and this is key, only with outcome-only rewards. So the model only gets feedback on whether the final answer is right or wrong, not on any intermediate step.
Okay. No step-by-step grading.
Right. And this RL training is then coupled with a curriculum that progressively increases the horizon length, the number of steps in the chain. This whole setup cleverly avoids that expensive need for step-level human labels or those complex auxiliary models you mentioned, which often just exist to score the intermediate steps anyway.
I see the structure, but I have to push back a bit on that core premise. If you only provide the final score, that outcome-only reward, how does the model possibly know which specific calculation, say 10 steps back, was actually the culprit when the final answer is wrong? Wouldn't a dense reward signal, where you grade every single step, be inherently more informative, more efficient for learning, even if it's pricier to generate?
That's the exact tension, the exact problem that H1 is designed to resolve. And the answer really lies in how the composition structure interacts with the curriculum. The composition ensures that every intermediate state calculation eventually gets tested implicitly by later steps in the chain. And the curriculum manages the difficulty so the model isn't overwhelmed. Think of it like this. If the model learns to reliably solve short chains first, it builds up two critical skills. We can define them technically as P, which is atomic reliability. That's just the accuracy on any single step.
Okay, basic step accuracy.
And sigmod, which is horizon-dependent reliability. This is the trickier skill. Managing and tracking intermediate values, keeping the overall state correct across the whole sequence. By mastering short chains first, where the reward signal is strong, they boost ZRDP. That gives the model a reliable foundation, which then allows it to start tackling the harder state management needed for improving sigmod.
Okay, that makes sense. So let's walk through this composition process. They start with these atomic tasks, the short problems. How do they actually link them? Is it complicated?
No, not at all, actually. They use what they call lightweight adapters. These are really simple deterministic transformations. Things like identity, which just means passing the number through unchanged, or scaling, maybe multiplying by 10, or a simple unit conversion. They're specifically kept simple so the transformation itself doesn't require complex reasoning. The goal is to ensure the model is only tested on the transfer and reuse of the value, not on figuring out some complex conversion logic.
Right, focus on the chaining, not the linking step itself.
Yeah.
Let's use that concrete example from the sources because I think it really brings this to life. The chain involved what? 3 steps? Wang's babysitting first.
Exactly. Step 1 calculates Wang's babysitting earnings. Let's say that answer is $6.
Okay, earnings are X.
Right. Then, using maybe a scaling adapter, $6 is multiplied by 10. That $10 becomes the input needed for step 2, Betty's wallet problem.
Got it.
The output of Betty's problem, let's call it dollars, is then passed perhaps via just an identity adapter to become a key parameter, like the page count for James's letter problem in the final step, step 3. So to get that final outcome-only reward, the model has to successfully solve Wang's problem, correctly track the value $6, multiply it by 10, then successfully solve Betty's problem using $10, correctly track the resulting value dollars, and then successfully solve James's problem using $.
Wow, okay. The dependency chain is absolute. One slip up anywhere, and the final answer is wrong.
Precisely.
And the curriculum approach is what makes training on this even feasible. You said they train stage-wise, starting with Horizon, 1 IDA's dollars, and then moving up.
Yes, $8, then 1 IDA's tutor, 3, 4, 5, 5, progressively advancing.
Why is that progression, the curriculum, so vital? Why not just, throw all the long, hard chains, say length 5 or 10, at the model right from the start?
Because of a classic problem in RL, especially with sparse rewards like this.
Yeah.
The vanishing gradient signal.
Mm.
Think about trying to train the model directly on the hardest, longest chain, let's say length of dollars. The probability of actually solving that entire chain correctly is mathematically linked to the chance of success on all the intermediate steps. So if the model fails 99% of the time on these long chains, which is pretty common early in training,
It almost never sees a positive reward signal.
exactly, it almost never succeeds, so it rarely gets that final reward signal. The model has almost no information, no gradient, to figure out which calculation, maybe 20 steps ago, actually led to the failure. The updates it tries to make have a vanishingly low signal-to-noise ratio, and training just collapses. It doesn't learn effectively.
Okay.
But by using a curriculum, they ensure the model starts where the success rate, let's call it 6-ish day, is high. That's at 20 FEI $1, the single-step problems. This gives the model strong, clear feedback, high signal-to-noise updates that reliably improves its atomic reliability, that p-value we talked about. And that sets it up for success when they gradually progress to longer sequences, which really start testing and building those crucial state tracking skills, the signal.
Right, okay. Here's where the analysis, for me, gets really compelling. The theoretical work in the paper. It shows that simply raising P, just making the model better at single steps, is fundamentally not enough for solving LHR. Is that right?
That's a key insight. You can have a model with, say, 99.9% single-step accuracy, but its long horizon performance can still completely collapse if its state tracking skill, its sigmage, decays badly across the sequence. It forgets or corrupts intermediate values.
So you need both high P and robust sigmage.
Precisely. And the theoretical payoff they showed for using this curriculum RL approach is staggering. They actually proved that it achieves an exponential improvement in sample complexity compared to training directly on the full difficult horizon from the start.
Exponential, that's huge.
It is. They mathematically reduce the required training time complexity, basically the number of examples needed, from exponential in dollars, the horizon length, down to polynomial in dollars.
Wow, that fundamentally changes the economic viability of training these kinds of long horizon reasoning models.
Absolutely. It makes it tractable.
That is a colossal saving. But okay, the real test, and maybe the source of some common skepticism around RL, is whether this training just helps the model get better at sampling knowledge it already possesses, or if it genuinely teaches it new reasoning skills it didn't have before.
A very fair question. And the empirical evidence here provides a really strong answer. It appears to teach genuinely new skills. They trained a model, a Quinn 2.53b instruct model, on this compositional data up to length 5. Okay, so chains of 5 linked problems. Then they tested it on unseen, even longer horizons, lengths 6, 7, and 8. And crucially, they tested it at a very high sampling budget. They used pass at 128.
Okay, let's unpack pass at 128 for listeners. That essentially means they allowed the model 128 attempts to generate the correct chain of thought solution for any given problem, right?
Exactly. It's not just testing the model's first guess. It's probing the absolute ceiling of the model's capabilities.
Mhm.
Can it find the right path at all, given many chances?
Got it. So it measures inherent capability, not just typical performance.
Right. And even at that absolute ceiling, the LHR curriculum-trained models perform dramatically better than standard RL baselines on these unseen longer chains. Since performance at high pass at K, like pass at 128, is generally thought to be bounded by the base model's inherent pre-trained capabilities. Well, this significant performance gap strongly suggests the model learned genuinely new horizon-dependent reasoning capabilities. It actually improved its SIGMAGE, its state tracking skill, through exposure to these structured dependency chains.
That really does feel like the breakthrough then, using synthesized, relatively simple sixth grade math problems to teach fundamental state management skills that apparently weren't strongly present before. But the million-dollar question, does this skill set learned on these synthetic chains actually transfer to hard, real-world problems, problems that weren't constructed in this explicit chained way?
And the generalization results are, frankly, quite remarkable. Remember, these models were trained only on chains composed from GSM-8K, which is accessible, pretty low-level math. Yet, this training generalized to significantly harder, high-stakes tasks that require complex, often implicit, long-horizon reasoning.
Like what? Give us some examples.
Okay, look at Olympiad math. The accuracy on AMY 2024, that's the American Invitational Mathematics Examination, a notoriously difficult competition for high schoolers.
Very tough problems, yeah.
The accuracy improved from just 5.10% on the base instruct model to 10.52% with this LHR-RL training.
Wow, double the accuracy.
More than double. A 2.06 times increase, purely from training on chains of much, much easier problems.
That really suggests the model didn't just get better at, sixth grade arithmetic. It fundamentally improved its internal logic and state management capabilities.
That's the strong hypothesis.
Did these Sigma skills transfer to other domains too, beyond math?
Absolutely. They saw significant out-of-distribution, or ODE, transfer across a benchmark called Reasoning Gym, which has diverse tasks. For instance, propositional logic accuracy, which inherently requires tracking assumptions and rules across multiple steps, it jumped from about 22.9% to 47.1%. Huge gain. Okay. Graph problems, which are all about tracking relationships across nodes and paths, improved from 15% to 22.5%. It seems the core ability to reliably track intermediate values and maintain state, learned from the simple math chains, immediately provided benefits in these other complex reasoning tasks.
And this also had unexpected benefits, perhaps, in areas we might not immediately connect to math problems, like long document understanding.
Correct. That improved state management capability transferred directly to long context benchmarks, too. They saw performance gains on things like Longbench V2 and another one called HashHop. These are benchmarks that require ultra-long context retrieval and often multi-hop variable tracing across thousands of tokens.
So if the model gets better at tracking a value across a short reasoning chain, it inherently gets better at tracking an entity or a fact across a long document context.
It seems very plausible that the underlying mechanism is related, yes. Better internal state tracking helps in both scenarios.
Okay, so wrapping up the practical takeaway here for you listening, this method seems to provide a clear, potentially scalable path for improving advanced reasoning using cheap, accessible data. You don't necessarily need a whole team of expert mathematicians annotating complex AE solutions step by step anymore.
Right, you might just need to cleverly chain together the simpler problems you already have access to, like GSM-8K.
Which brings us neatly to the cost-compute trade-off they analyzed. Because in the real world, that short horizon data, like GSM-8K, it's essentially free and abundant. But actual long horizon data, expert annotated stuff, that's the limited and expensive resource.
Exactly. So the researchers wanted to know, can you effectively substitute that data scarcity with computational budget? Can you trade dollars spent on data for dollars spent on compute?
And is the final accuracy fundamentally dependent on having like a perfectly balanced mix of short and long chain samples? Or can you skew heavily toward the cheap short samples and still get there?
Well, they found something quite interesting. You can achieve the same final accuracy using data distributions that are highly skewed toward the cheaper short samples compared to using a uniform distribution with more long samples.
Okay, that's good news for data acquisition costs then.
It is. However, there's a critical trade-off.
Right.
Achieving that same top performance level, but using a cheaper skewed data distribution requires increasing the total training compute budget. You need more FLOPs, more processing power.
Ah, okay. So you save money on data, but you spend more on compute time or hardware. That's a crucial insight. But I have to ask about the sort of real world implications there. If you're substituting data costs for computational cost, are these kinds of gains only really accessible to the major labs with massive compute resources? For smaller research teams or companies, is this actually a feasible trade-off?
It does potentially raise the barrier to entry slightly in terms of raw compute needed, that's true. But the insight itself remains valuable for designing training systems, regardless of scale. If your goal is maximizing performance on LHR, this analysis tells you exactly where to focus your budget. Invest in maximizing the volume of cheap, short compositional data you can generate or acquire, and then accept that you'll likely need more compute cycles to iterate over that data effectively to reach peak performance. It fundamentally shifts the resource allocation challenge away from expensive, potentially slow human labeling towards more scalable machine computation.
Right. Okay, so stepping back, what does this all mean? What's the big picture here?
Well, I think the H1 method fundamentally addresses, or at least offers a very promising path to addressing the scaling issue in long horizon reasoning. By cleverly using synthetic composition of simple problems in curriculum learning, powered only by final outcome rewards, they achieved what looks like an exponential speed-up in training efficiency for LHR. And crucially, this method seems to unlock genuine new state management capabilities in LLMs. It provides strong evidence that even simple data, if structured correctly through composition and curriculum, can lead to complex, high-level reasoning skills. And importantly, these skills transfer broadly across difficult mathematical, logical, and even long context domains.
Yeah, what's really fascinating to me is that the theoretical work suggests this curriculum learning strategy, just using those simple outcome-only rewards, it scales equivalently to using dense per-step rewards,
Yeah.
but without the enormous annotation costs. So, okay, here's a final provocative thought for you, for the listener. Currently, H1 focuses on these simple serial chains, right? Problem A feeds into problem B, which feeds into C, and so on. Linear. What if we could effectively apply this composition and curriculum strategy to more complex problem graph structures? Think about structures involving, I don't know, branching dependencies, conditional execution based on intermediate results, maybe even multi-threaded logic. If we could structure training like that, what currently impossible multi-step problems might LLMs solve next? Could this push them towards genuine strategic planning or even aspects of scientific discovery?
That definitely pushes us well beyond simple linear math problems
Mm,
into truly hierarchical, maybe even nonlinear reasoning. That's a very, very compelling direction for future research.
absolutely. Food for thought. That's it for this deep dive. Thank you for joining us, and we'll see you next time.